Hello, and today's purpose of the day is I can graph an exponential function and determine the y value given a specific x value of an exponential function. So just a warm-up and recap of exponents, let's look at the first two warm-up problems. So on number 1/5 to the negative second power means I need to distribute that -2 to both the numerator and denominator. So I have 1 to the negative second all over 5 to the negative second, and then I can't have negative exponents, so what I need to do is I actually need to flip both of them to make my exponents positive, and I end up getting 5 squared over 1 squared, and 5 squared is 25, 1 squared is just 1, so my answer would be 25. Number 2, 2 times 3 to the negative fourth. Now I need to first simplify 3 to the negative fourth. So 3 to the negative fourth over 1 needs to be simplified. I can't have a negative exponent, so I need to flip those. So what I have is 2 over 1 times 1 over 3 to the fourth, and 3 to the fourth is 81. So I get 2 times 1, which is 2, over 1 times 81, which is 81. So my answer here would be 2 over 81. Now this warm-up will help us today in these exponents, because a lot with exponential functions, what we're dealing with are certain exponents, and they could be negative and they could be positive, and so we need to make sure we simplify those correctly. All right, let's get started. An exponential function is a function in the form of y equals a times b to the x, where a cannot be 0, b is greater than 0, but b cannot equal 1. And we'll go through why those certain numbers need to be what they are. But let's look at a little bit more. A base is a constant, and now your exponent is the variable. So that will be something that constantly will change. And then to make this graph, we will make it with a smooth curve. So if I have, just a graph, and I want to graph my exponential function, it could look like this. It could look like this. It could go the other way. Right, we could open downward. Okay, an exponential function has a smooth curve. What it doesn't have is it doesn't have a specific stopping point and then continues on. It's always made by a smooth curve. Let's look at graphing the example y equals 4 to the x. So here my base is 4. Okay, so now when I go to my table, I am going to plug in these different x values right here in my table in for my exponent x. So the first one would be y equals 4 to the third, right? And 4 to the third is 64. Okay, our second one would be 4 squared. Again, I'm just plugging in these numbers into my variable, again right up here. So 4 squared is 16. Then 4 to the first, which would be 4. 4 to the 0 power, again, anything to the 0 power is 1. Okay, now we get to the negatives, and I have 4 to the negative first. Well, I really can't have 4 to the negative first, so I'm going to move this over a little bit. 4 to the negative first really means I need to flip that over my fraction, and what that would equal would be 1 over 4 to the first, and 4 to the first is just 1, so this is really just 1/4. Right? Now 4 to the negative second is really 1 over 4 to the positive second, and 4 squared, 4 to the second, is 16, so this is 1/16. Then the last one, 4 to the negative third, let's fix that. 4 to the negative third is really 1 over 4 to the third, and 4 to the third is 64. So if you notice about your table, right, like 4 to the positive third is 64, 4 to the negative third is 1 over 64. So you're going to maybe start to see a pattern as you go through making your tables that will help you not only determine what your graph will look like, but how to fill in your table. Okay, so now if we go and actually graph this, we're going to go to our graph paper, and I'm going to plot all of these points on my table onto my graph. So on my graph, I've plotted the points for my table, and as you can tell, this graph is continuing to rise upward at a very fast rate. But as you notice, on the left-hand side of my graph of the y-axis, so right over here, my graph is getting closer and closer to the x-axis, but it'll never actually get there because if you look at these values here on our table, I'm going to keep continuing to get smaller. 1/4, 1/16, 1/64. It'll keep getting smaller and smaller, but it won't ever actually ever equal 0. No matter what number we would plug in for x, what negative number, 4 to the negative 100th, 4 to the negative 500th, it will never get to 0. So as you can notice with this graph, it's actually never going to get to 0. So I'm going to draw in a dashed line, and we'll talk about what that dashed line is in just a little bit. So more about this problem. Let's figure out the y-intercept. So when I plug in 0 for x, what was y? That was 1. So I highlighted in my table. So I will go to fill out a little bit more about this function, and the y-intercept is 0, 1. All right, the domain. As we look at our x values for the domain, does it matter what we plugged in into our table for x? No, it didn't matter, and if you look from left to right on our graph, our arrows continue. Our arrow will continue to rise upward and go to the right, or on the left-hand side, it will continue to get closer and closer to 0, and it will go on forever. So the domain is all reals. So I will say x is between negative infinity and positive infinity. Again, or I could, represent with the all real sign or write out all reals. All of that would be okay. Now the range. So now as we look from, highest to lowest, we're going to notice that this arrow here is going on forever and will continue to rise up and, continue to get wider. So that's going up to positive infinity. But now what's the lowest value that our graph could be? Well, again, if you look at our table here, what we already talked about, the numbers get very, very close to 0, right? We get small fractions, but they will never actually be 0. So our range is y is between 0 and positive infinity, and it can never equal 0, again, because if you were to plug in any value, any large negative value in for x, as you can see from our table, it won't actually ever get to 0. All right, now let's try approximating certain exponents from our table. So let's approximate 4 to the 0.3, right? And we don't typically see decimals as exponents, but we're going to talk about those right now. So 4 to the 0.3, I would look in my table, and 0.3 is be right here, right between 0 and 1. So we know if we plugged in 0.3, right there, I should say, right, between 0 and 1 there, so then we're looking at these two values for y. If we plug in 0.3, we can approximate that. That'll be between 1 and 4. 0.3 is a little bit closer to 0, so I would maybe say it's closer to the 1 than it would be to the 4. So what do you think would be a good value to approximate? I think a good value to approximate could be any of the following. It could maybe be 1.5, 1.5. It could be perhaps maybe 1.75. It could even maybe be 2. Right? All of those would be good estimates. And then let's actually use our calculator and let's type in 4 to the 0.3. What do you actually get? I get approximately 1.52. So using our table, we can approximate values to an exponent that may or may not be integer values. Okay, a couple things to think about. How is the exponent in this equation different than that in a quadratic? Well, in this case here, the exponent is a variable, right? Exponent is a variable. Also, with quadratic, the highest exponent that is 2, or here, the exponent is constantly changing. So just to note, quadratic exponent is only 2, where here with a exponential, it's constantly changing. For this specific function, can the value of y ever be 0? No, not in this case. And we saw that with our table here, that our values were getting very, very close to 0, small fractions, but would never actually be 0. Now what that is called is here, that 0 will never be in this function, is that's called an asymptote. And an asymptote is a line that a graph approaches. Here, if I scroll back up to our graph here, and you see this red dashed line right? The x-axis, that also is 0. And that's an asymptote for this graph because the graph will never actually reach 0, but it will get very, very close to 0 as it continues to continue with its equation, with its graph. Okay, let's look at one more example of graphing an exponential function and answering a few questions about it. Now this function that we are going to graph is y equals 1/4 to the x. So the last one we went through was y equals 4 to the power of x. Now here it's 1/4 to the power of x. So we're going to see how if we have a number greater than 1, what that graph looked like, and that again was on the last example. And now here, if we have our base that's less than 1, what type of graph will that look like? And again, here our base is 1/4. On the last graph, it was 4. All right, so let's look at filling in our table. So if I plug in 3 into my exponent, I have 1/4 to the third power. So 1/4 to the third power means, I distribute that 3 to the 1 and to the 4. 1 cubed is just 1, 4 cubed is 64. So this would be 1/64. Okay, same thing for if I plug in 2, 1/4 to the second. I distribute that 2, 1 squared is 1, 4 squared is 16, so 1/16. 1/4 to the first, right? Distribute that 1, I'm just going to get 1/4. Anything to the 0 power is 1. Now 1/4 to the negative first. So now if I distribute that, I get 1 to the negative first over 4 to the negative first. So I need to flip those, and that will give me positive 4 over 1. Okay, and if I continue to see that pattern, I know 1/4 to the negative second means I'll have to flip both of my numerator and denominator again, and squared gives me 16, so this one will be 16. 1/4 to the negative third, distribute that negative 3, now I'll have to flip both of them, and then 4 cubed is 64. Again, you can see in our table, the 3 and the negative 3 values for x, their output y, are just opposites, right? 64 and 1/64th. 2 and negative 2 would be 1/16 and positive 16. So just looking at those comparisons and figuring out how to simplify your table will help you as you go through more and more exponential functions. Okay, let's graph these on our graph, and I will do so as well. So there's my graph with the points from our table plotted. So the y-intercept of this graph, again, where x is 0, it would be 1, so 0, 1. Domain will be all reals. Again, I could have plugged in anything I wanted to in my table for x, and as I look at my graph, my lines will continue to, keep going on throughout the sides, and we'll be able to hit any value I really wanted to plug in for x. So the domain will be all reals. So x is between negative infinity and positive infinity, or all reals. The range, as you notice, our graph is still going up to positive infinity, even though it appears to be going a different direction. So the range, I'm still going to positive infinity, and what's the lowest portion of this graph? Well, it can never equal it, but it appears on our graph as if it's getting very, very close to 0, but it won't actually ever get to 0. And again, that is known as our asymptote here. All right, now let's approximate 1/4 to the negative 1/5. And now on the last example I mentioned, let's just use our table, right? So negative 1/2 would be between negative 1 and negative 2, or here my output would be 4 and 16. But we actually could also use our graph. And maybe you thought of that on the last example. So if I wanted to look at where negative 1/2 was, here is, negative 1, so negative 1/2 would be, somewhat right there. So we can double check our graph too if our answer seems reasonable from our table. So if I were to plug in negative 1/2, and if I didn't have a calculator, 1/4 to the negative 1/2, I might approximate as, well, it's between 4 and 16, and, the negative 1.5 is directly between the negative 1 and the negative 2, so what's perhaps right in the middle of 4 and 16? Well, I would say 8, right? I would surely say 8. If you said 9, that would be a good estimate too, but I would say 8. And now if we actually use our calculator to find out what that is, what do you get? We get 8. So we had a match. And if we look at our table, we could see here negative 1/2, could be very, very close to being 8 as well. So that's how we know that we're right. Okay, so This slide, along with the next two, we are going to save to do in class together. So again, it will be a review of linear, quadratic, and exponential functions and comparing certain features to each function. And save this part of your notes for in class. And save this portion for your notes in class. Thanks for listening. Have a great day. Bye-bye.